Let's start things off with a puzzle. Say I give you a bounded segment of the x-axis, maybe the open interval from 0 to 1. So all real numbers strictly between 0 and 1, but not including 0 and 1 themselves. Can you draw the graph of a continuous function that has no finite maximum on that interval? That is, can you draw a single continuous curve moving from left to right that has no highest y-coordinate? Many of the regular kinds of curves you could draw wouldn't be able to do this. But if you've seen enough graphs in your life, you might have an idea. Try the function 1 over x. Its graph forms a vertical asymptote at x equals 0, meaning the height of the graph grows without bound as x approaches 0, though the graph never actually reaches x equals 0. Thus, it has no finite maximum. Alright, but what if I require the graph to actually touch both x equals 0 and x equals 1? That is, the graph must actually contain a point with x-coordinate 0 and another point with x-coordinate 1, in addition to all the values in between. So no funny business with asymptotes or holes, but it still needs to be a single continuous curve. Can you draw a curve that has no highest point now? Not so easy, is it? It's tempting to try and fit an asymptote somewhere, but anywhere you put one will result in a discontinuity, since the function now has to be defined at the actual asymptote point itself, and we're not counting infinity as a number here. So it seems like we're forced to actually have a legitimate highest and lowest point on the graph. We can't avoid it. But is it actually impossible, though? How do you know? If you'd never seen an asymptote before, you might not have thought of that solution in the previous case. So how do you know there's not some similarly clever trick that will allow the function to avoid having a max or a min in this case? Well, it's questions like these that the concept of compactness helps solve. It's one of the most important concepts in topology and analysis, but it can feel a little mysterious and also contrived when you first learn about it. So what is compactness intuitively? And why is it so fundamental to so much of modern math? Compactness is a property of shapes, or to be more precise, of sets of points in some kind of space. This time, for a change, how about we just take a look at the formal definition right off the bat? A pretty standard definition of compactness would go something like this. A subset K of a topological, or metric, space is called compact if every open cover of K has a finite subcover. Alright, now let's go and, unpack this definition. First of all, it mentions a topological, or metric, space. What is that? I went over this briefly in my video about connectedness, but just to recap, remember in topology, all shapes, curves, etc. are thought of as a collection, or set, of points. And any set of points S divides the space it lives in into 3 other sets. The interior of S, consisting of all points that can be enclosed in a ball that's also contained in S. The exterior of S, consisting of all points that can be enclosed in balls that are completely disjoint from S. And finally, the boundary of S, points where any ball containing them, no matter how small, are only ever partially inside or outside S. The critical thing to note is that a set may or may not include its boundary, or can even include just part of it. A set that includes all of its boundary is called closed. A set that includes none of its boundary is called open, and a set that includes only part of its boundary isn't special enough to get a name. So getting back to our definition, without going into too much detail, a topological, or metric, space is just a space where concepts like open, closed, interior, exterior, boundary, and so on make sense. The important sets to pay attention to regarding compactness are the open sets. Those are sets that only consist of interior points, which is important since it means they always have to be a little bit fat, since any points inside them have to be able to be enclosed in balls that are also inside the set. This brings us to the next part of the definition, open covers. This one is pretty straightforward. An open cover for a set is a collection of open sets that collectively cover the target set. There could be finitely many of them or infinitely many, and can individually have any size. A subcover is just a subcollection of these open sets that still manages to cover the target set. Note we also include the original cover itself as one of its subcovers. So putting all this together, a compact set is a special set where, for any, possibly infinite, collection of open sets you come up with to cover the set, you can always select a finite subcollection of them that will still cover that set. Note that this isn't the same as saying the set can be covered by finitely many open sets. That's actually true of all sets. Just pick a big enough open ball to cover it. Or, if it's an unbounded set, just use the entire space itself, which counts as an open set. No, this is saying something more subtle. It's saying that if you give me a potentially crazy complicated collection of open sets that covers the compact set, I can always cover the set using only finitely many of the open sets you gave me. Or to put it another way, any infinite collection of open sets that together cover a compact set always overcovers it. You can always get away with a finite subcollection. And that's it. That's all a compact set is. Not too crazy a concept once you've digested it. But even so, it's not very clear yet what kind of sets would fit this description. In fact, right out the gate, it sounds like they'd have to be pretty strange and complicated, right? And furthermore, why would sets with this property be that interesting or important anyway? So let's see if we can get a better intuitive sense of what these sets are and what they can do. The simplest kind of compact set is just a finite set, a collection of finitely many points. Because if I cover a finite collection of points with open set blobs, I can just go point by point and select one open set from the cover that contains it. And in the end, I'll have selected at most one set per point. Though in practice, maybe fewer, since some of the open sets I selected might cover multiple points. This actually gets pretty close to the heart of what compactness is meant to do. Compact sets sort of simulate finite sets for topological purposes, in the sense that certain tricks or techniques that work on finite sets also work on compact sets. But more on that later. Beyond finite sets, the first examples of compact sets you're likely to be introduced to are closed and bounded sets of the real number line. So the closed interval 0 to 1 we saw at the beginning of the video is an example of a compact set. The fact that closed and bounded sets of real numbers are compact is known as the Heine-Borel theorem, and is a foundational result in analysis. I won't go through the proof of it here though, since it takes a little finesse, and I also don't think it sheds that much light on the broader question of how we should intuitively interpret what compactness means. For that, I think it helps to turn to an alternative description of compactness called sequential compactness. To understand it, think about a sequence of points. Depending on the sequence, it may or may not converge toward a limiting point. If it doesn't converge, it may fail by diverging off to infinity, or by wandering aimlessly around without approaching anything. But in this second case, you can sometimes extract a convergent sequence out of it by selectively ignoring certain points in the sequence. Here's an example. Consider the sequence which just alternates between 0 and 1. This sequence is divergent since it never makes up its mind, so to speak, about whether it's approaching 0 or 1. But if we selectively ignore every other term, we get a sequence that just looks like an endless string of zeros, or 1s, which of course converges to 0, or 1. That's an extreme example, but more generally, if you have a sequence that diverges, but nevertheless forms clusters in certain spots, then by carefully throwing out points not in the clusters, you can sometimes extract a convergent sequence out of it. What you might call a convergent subsequence. Now, bringing it back to compactness, it turns out a set is compact if and only if every sequence of points that stays within that set has a subsequence that converges to a point also in that set. That is, a compact set is a set which forces any sequence of points within it to form clusters that converge toward a point also within the compact set. This is called sequential compactness, and it's equivalent to the standard notion of compactness, except in certain more unusual topological spaces, which we won't worry about here. From this new perspective, we can perhaps get a sense for how to intuitively think about compact sets by studying the different ways a set can fail to be sequentially compact. or in other words, the different ways to prevent a subsequence from converging. The simplest way is just to have the original sequence diverge off to infinity. Then any subsequence will also diverge to infinity, meaning any set containing such a sequence won't be compact. So the first requirement of a compact set is that it should be bounded. It can't be infinitely big or elongated. The second way to stop a sequence from having a convergent subsequence is to have it approach a hole or a missing point in the set, which could either be a gap in the interior of the set or a missing boundary. Then every subsequence will also approach that hole and will fail to converge. So the second requirement for a set to be compact is that it should not have any such missing points. It should be complete. With the two requirements of boundedness and completeness, it might seem like we've covered every failure case. But there is actually a third, very subtle way a sequence can avoid having a convergent subsequence. But to see it, we'll need an infinite dimensional space. That may sound intimidating, but there are actually some relatively simple examples. Think about it this way. Any point in a two-dimensional space can be described with two numbers, x and y. Likewise, a point in a three-dimensional space can be described with three numbers, x, y, and z. So a point in an infinite dimensional space can be described with an infinite list of numbers, a1, a2, a3, and so on. To keep things a little simpler for this example, I'll restrict the space to only include lists that eventually end in an endless string of zeros. With this in place, consider this sequence of points, which are actually lists. Each list contains only a single one surrounded by nothing but zeros, where the nth list in the sequence has a 1 in the nth place. This sequence of lists is bounded. All of them are a distance of 1 away from the zero list. But it doesn't converge. This sequence of lists doesn't approach any list. You might think it converges to the zero list, since any particular slot in the lists eventually becomes a zero. But from a strictly topological point of view, it doesn't approach the zero list, since any list in our sequence stays a distance of 1 away from the zero list. And naturally, any subsequence will suffer the same fate. In effect, we have a sequence of points that endlessly explores all the infinitely many coordinate axes of the infinite dimensional space, while always staying a fixed distance away from the origin. So it avoids approaching anything by kind of traveling through infinitely many dimensions. Sounds like bad science fiction, but it's true mathematics. The requirement we'd need to impose on a set to prevent this is called total boundedness, and it basically says that your set can be covered by a finite number of balls of any given fixed size. In our familiar finite-dimensional Euclidean space, this is the same as just ordinary boundedness, since any bounded blob can always be covered by finitely many balls of any fixed size, no matter how small. It may take a lot of them if they're really small, but it's always a finite number. Not so for our infinite dimensional set, though, since if I surround each point in our sequence with a ball of radius 1/4, for example, all the balls will be disjoint from each other, since every list in the sequence is a distance of more than 1/2 away from every other list. So the set this sequence of lists lives in would not be totally bounded. With total boundedness in place, we finally actually got enough to force every sequence in a set to have a convergent subsequence. That is, to be compact. Because there's a theorem that says a set is compact if and only if it is complete and totally bounded. So this is how I like to think about compactness intuitively. A set is compact if it's small enough and solid enough that there's no way for a sequence inside it to escape to infinite distance, escape into a hole or edge, or escape through infinite dimensions. In ordinary finite-dimensional Euclidean space, this corresponds precisely to the sets that are closed and bounded. But as we saw, that's not always enough for more exotic spaces. So that's how I view compact sets intuitively. But even so, why are such sets so important to analysis and topology? What do they let us do? Let's look into that now. One of the main reasons compact sets are so nice is they often provide a way to take properties that hold locally on the set and extend them to apply globally on the entire set. That may sound a little vague, so let's do an example. Remember the puzzle at the beginning of the video, where I challenged you to find a continuous function on the closed interval 0 to 1 that didn't have a maximum? Well, it turns out it is indeed impossible, and it comes down to the fact that the closed interval 0 to 1 is compact. Every continuous function defined on a compact set attains both a maximum and a minimum. This fact is known as the extreme value theorem, and to show how compactness plays a key role, we'll prove a slightly weaker version of it, that any continuous function defined on a compact set is bounded, meaning the function's outputs have both a finite upper bound and lower bound, but we won't require the function to actually reach those bounds. Just so we have something concrete to look at, let's take that compact set to be the closed interval 0 to 1. To begin, consider an arbitrary real number x in the interval 0 to 1. Since our function f is continuous, it loosely means small changes in x result in relatively small changes in f of x. In fact, if I restrict the variability of x to a small enough interval, call it a delta interval, I can force the function's outputs, f of x, to stay within certain bounds, like, I don't know, a distance of 0.1 from where it started. So in essence, I've defined a certain open interval around x, where the image of that interval after applying f to it results in a bounded interval in the output space. In other words, f is bounded locally around x. Can you see where this is going? We can construct one of these little delta intervals around every single point x in the domain, creating, potentially, an uncountably infinite collection of delta intervals that together cover the domain 0 to 1. But since the domain 0 to 1 is compact, it means we've overcovered it. And so we can reduce down to a finite subcollection of these delta intervals that still cover all of 0 to 1. But by construction, the function f is bounded on each of these remaining delta intervals. And since there are only finitely many such delta intervals, there must be a finite overall upper bound for f. Just take the highest upper bound for f among all the remaining delta intervals. And likewise, we can find a finite overall lower bound. Thus, f is bounded on the entire interval 0 to 1. We've taken local boundedness and turned it into global boundedness. But notice how this proof falls apart if the domain isn't compact, like on the open interval 0 to 1. If we try the same trick here for the function f of x equals 1 over x, we'd find the delta intervals for the x values get thinner and thinner the closer we get to x equals 0 in order to keep the same local bounds on y, since the function is so steep there. It doesn't take much variability of x to get y to vary beyond our maximum chosen tolerance. And here, there'd be no way to reduce to a finite subcollection of these delta intervals, since we'd truly need an infinite number of them in order to cover the interval all the way down to x equals 0, since they'd be getting thinner the closer we get. And if there are infinitely many delta intervals, we can't guarantee that there is a single delta interval that yields the highest possible upper bound for the function f. And for the function 1 over x specifically, there definitely isn't one. That's an overview of what compactness is and why it's so important and useful. Indeed, you'll encounter the concept over and over again in higher math, where it tends to be an important ingredient in enabling many powerful constructs such as function spaces, where functions can be treated like infinite dimensional vectors and studied as such. According to some, being able to understand compactness might even make the difference in being able to participate effectively in higher math. Much of modern math is built on compactness. And if that's true, I hope this video has made it a little more accessible. But speaking of making math more accessible, one of the best resources I've encountered for providing a thorough and enjoyable way to learn math is this video's sponsor, Brilliant.org. One of the main applications of compactness is in the rigorous study of probability. And if you need a way to learn or brush up on your probability fundamentals at your own pace, Brilliant offers several courses on it featuring their signature interactive lessons. like their Intro to Probability course, which I like a lot as they have you build and run simulations right in the lesson, helping you get a real visceral feel for how it all works beyond just the theory. Beyond probability, Brilliant has a wide selection of thousands of other lessons in math, computer science, and data science, with new lessons added every month covering both basic and advanced topics. And Brilliant goes out of their way to make sure each lesson feels friendly, fun, and inviting, a spirit similar to how I try to make my own videos. You can get started with a free 30-day trial by heading over to brilliant.org/morphocular, and the first 200 of you to sign up will get 20% off an annual premium subscription. So thanks to Brilliant for sponsoring this video, and I'll see you in the next one.